Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue the discussion on the characteristics of component. Earlier on, I have finished the discussion of a passive component like resistor. For this video, I'm going to concentrate on inductor. The next few video, I'm going to concentrate on capacitor. However, let's focus on this video. The objective of this video is to how to design the coil into a specific inductor value. Later on, you will realize that there are three parameters that will determine the values of an inductor. Number one, the length of the coil. Number two, the radius of the coil. Number three, the numbers of turns. Okay, these are the three parameters that will contribute to determine the value of the inductor. This will be the Part 4C series discussion. Okay, all the Part 4 series will be on inductor. So stay tuned over here to receive more information on the discussion on inductor. Next will be on capacitor. This is my email. If you have any question regards on today's discussion, please drop me an email. Before I continue, I'd like to urge you guys to support this channel by pressing the like and subscribe button. Please also turn on your notification bell in order to receive more information from this channel. Once again, guys, I really appreciate your strong support. Thank you so much to stay with me for so long. Thanks. Firstly, okay, let's understand how these three parameters affect the value of an inductor. The radius, okay, where is the radius? Okay, you can see from here, this is the diameter. In order to obtain the radius, will be diameter divided by 2. So we can actually obtain the radius. Next will be on the length. Okay, where will be the length? Okay, the length is basically measured from here to here. Okay, so this will be the length. So this is the length as indicated here. Next will be the numbers of turns, how many turns there will be. Okay, let's take a look over here. So there will be 1 turn, 2 turn, 3 turns. So over here you can see that there will be 3 turns. Okay, so if we have this cross-section view, so imagine here we cut open here. So this will be the radius. Okay, so from here the diameter divided by 2 will become the radius. Okay, the length from here to here. So this is the length from here to here. Okay, all these will be indicate the numbers of turn. Okay, the n value here. So we can actually obtain the inductor value by substitute the three parameters. Firstly, the radius, the length, and the numbers of turn, as you can see from here. Okay, so R stands for the radius, N stands for the numbers of turn, and the length, okay, will be the length of the coil. So from here, you can easily calculate the value of the inductor. Okay, for best Q, okay, the length is good to be close to 2 times the radius. So in order to achieve a very good Q, this is what I will recommend. Okay, make sure your length will be close to 2 times the radius, or simply L is equal to the diameter. Let's understand by doing an example. Okay, so this will be the example 1. In this example 1, I will give you all the 3 parameters, and from the 3 parameters, okay, we can compute the inductor value. Okay, let's start. Okay, what is the inductor of a 20-turn coil? Okay, so from here, I know that N is equal to 20 on a half-inch diameter. Okay, so if we convert half-inch into centimeter, it will be 1.27 centimeter. Formed with a coil length of 2 inch, 5.08 centimeter. Okay, so I have all the 3 parameters. Okay, I've forgotten to highlight this on the previous slide. Okay, all these parameters that you're going to substitute, okay, make sure they are all in centimeter. Okay, for example, the radius must be in centimeter. The length of the coil must be in centimeter. Then you can substitute inside here. So therefore, in this equation here, you can see that I actually convert the inch into centimeter. You can see from here, inch into centimeter, then I can work out on this equation here. Okay, so these are the 3 parameters that is given in the question. So I know my numbers of turn. Okay, the diameter is 1.27. Again, if I want to obtain the radius, I can simply use diameter divided by 2, which will give me 0.635 centimeters. I also have the length, which is 5.08 centimeters. Okay, so how can we compute the inductor value? Okay, so this is the formula that I shared with you on the previous slide. So what we need to do is we substitute all the value here. So the radius is 0.635. You can see that this is in centimeter. So this will be the radius in centimeter. The numbers of turn will be 20. Okay, this 22.9 is a fixed constant, so don't worry, just put 22.9 multiplied by the radius, okay, plus 25.4 multiplied by the length of the coil, which is 5.08 centimeter. So from here, I can compute that the value of the inductor will be 1.12 microhenry. So from this example 1, okay, if I can know these 3 parameters, I can easily calculate my inductor value. Next, on example 2, okay, it's slightly different. Okay, so basically I rephrase it. How many turns I need in order to achieve a certain value of inductor? For this question here, for example, I need to calculate how many turns I need in order to achieve an inductor value of 20 microhenry. Okay, so I have this diameter 5 centimeter and I have the length which is 3.8 centimeter. So this is the cross-section view. Okay, the length which is 3.8 centimeter, diameter is 5 centimeter. So again, I will be able to achieve all the value here. So earlier on, the question tells me that I need to achieve an inductor value of 20 microhenry. Diameter is equals to 5 centimeter. I can get the radius, which is 2.5 centimeter. Diameter divided by 2, which is equals to the radius. I also will be able to obtain the length, which is 3.8 centimeter. So let's calculate. Okay, so this is the equation that I shared with you earlier on. So the question given to me that inductor value must be equals to 20 microhenry. So I need to know how many numbers of turns I need in order to achieve 20 microhenry, the inductor value here. So I need to rearrange the formula. So you can see from here, I do a cross multiply. So L multiplied by all these here, divided by R squared, okay, because R squared moved to the other side here. So because this is N squared, okay, I need to do a square root over here. So what I need to do is I substitute all the values here. So for example, the radius will be 2.5 centimeter. Okay, and I know the length, okay, which is 3.8 centimeter from this diagram here, 3.8 centimeter. Okay, the radius again is 2.5 centimeter. I can compute that the numbers of turn, okay, which is 22.18. However, for the numbers of turn, I can't afford to have decimal point. So I make it as close as possible. So the numbers of turn will be 22 turns. Okay, so from here, if I can achieve 22 numbers of turn, okay, with a diameter or with a radius of 2.5 centimeter, the length 3.8 centimeter, I will be able to achieve an inductor value of 20 microhenry. Next, on example 3, here, this question here, I break into 2 parts. So I will do the black color wording first, after that followed by the green color wording. Okay, so let's focus on the first part first. An inductor has a reactance XL of 250 ohm and a series resistor of 2.5 ohms. Find the component Q and the equivalent parallel resistor RP of the inductor. Okay, so let's focus on this first. Okay, so this is the equivalent diagram of an inductor. Okay, in order to do more analysis, okay, so let's ignore this distribute capacitor first. Okay, so let's ignore this distribute capacitor. So this will be the equivalent circuit of an inductor. Okay, the question given to me, the reactance is equals to 250. Okay, and the RS is also given in the question, which is 2.5 ohm. Okay, since this L and R is connected in series, okay, so I can compute the Q value in terms of series resonator. So this Q is equals to X over Rs. So with these 2 parameters given, I can easily calculate the Q, component Q of the inductor to be equals to 100. Okay, so this is how I obtain the component Q of an inductor. Okay, by having the reactance, okay, I can actually measure this okay, in a spectrum analyzer. Okay, if not, you can also have this impedance analyzer to measure this reactance and also the resistance value, which is typically will be given in the data sheet. Okay, so next I need to find my parallel resistor. Okay, so what happened here is basically the series, I need to convert them into parallel. So this become the parallel equivalent circuit. Okay, so in terms of series, okay, you can see here earlier on will be series. Okay, how can I convert them into parallel? Okay, if the component Q, okay, they are actually greater than 10. Okay, so these are the two assumptions that I can meet. So if the component Q, which I have calculated earlier on, which is 100, okay, I can actually make these two assumptions. Okay, so when we're having these two assumptions, okay, I actually can calculate the parallel resistor. Okay, so this Q squared, okay, the component Q is equal to 100 multiplied by 2.5. I can compute that the parallel resistor of an inductor, which is equal to 25 kilo ohm. Next, okay, we're going to focus on the green color. If the inductor is shunt with a 50 kilo ohm resistor, Rshunt, okay, to form a circuit, okay, what is the total parallel resistor RL and the circuit Q of this circuit? Okay, so this is the equivalent diagram that I have calculated earlier on. Okay, instead of series, okay, I use the parallel. So another parallel resistor is actually shunt together with the inductor. Okay, so the question given to me that the inductor, the resistor to shunt with the inductor will be 50 kilo ohm. So I know that this Rshunt is 50 kilo ohm. So these two resistors add okay, to form the RT. Okay, so we know that these two resistors, they are actually connected in parallel. So how to calculate the total resistor, okay, will be these two resistors in parallel. We can use this equation, okay, to compute the total resistor value, which is equal to 16.67 kilo ohm. Next, I need to find the circuit Q, okay, because now I add external component. So instead of component Q, it become a circuit Q. Circuit Q means that the total, okay, that is contribute here. So how can we find the so-called the circuit Q? Okay, you can see that they are all connected in parallel now. So I need to use my parallel resonator to calculate. Okay, so this is the circuit Q. R will be the total resistor over XL. Okay, remember I told you that if the R is more than 100, or sorry, more than 10, okay, I can assume they are the same. So from here, I can calculate that the circuit Q is equal to 66.68. Okay, so with this, okay, I like to end my discussion. Over here, you can see that with the three parameters, for example, the radius, the length, and also the numbers of turns, will indicate the value of the inductor. In this example, I have done a quick conversion, how to convert a series, okay, by right, the equivalent circuit of a inductor, they actually look like this. Okay, I actually omit away my distribute capacitor, okay, which result in this equivalent circuit of an inductor. Over here, I have shown it to you how to convert a series resistor into a parallel resistor. So this becomes the resultant parallel equivalent circuit of an inductor. Okay, with this, I'd like to end my discussion. Please help to like and subscribe. Once again, thank you so much, guys, for your strong support. See you guys soon. See you. Bye-bye.